We've so far been analyzing our systems only in transfer function form, but we do want to remember that we had the alternate modeling method of state space. So we want to see how does our analysis work in state space, and then we will return to mostly doing this in transfer function form. So first, let's remember what our state space model looked like. It was these two matrix equations. We had our first order ODE, the x dot. We had our A and our B matrices that used our states x and our inputs u. And then we had our observables y that had the matrices C and D associated with it. And we talked previously about how do we go from state space form into transfer function form, and we can also go the other way as well. So we can convert to transfer function if we know our A, B, C, and D matrices by some matrix algebra here, doing an inversion, etc. We can take our matrices and go to our transfer function form. Now we have this SI minus A term here that we are inverting. I'm not going to go deep into the math here, into the linear algebra, but we can see that we are dividing by this thing and by this quantity. Effectively, it's really a matrix inverse. It's not real division, but we kind of have an equivalent here of dividing by something. And when that something is 0, we're going to have poles, more or less, in this kind of stretched analogy. So we can look at here is what are the values that make SI minus A, the determinant of that, 0. And really what we're seeing here is a parallel to what are the poles in our transfer function system. So really the idea here is that the eigenvalues of A are the poles of our transfer function. And this is coming from really the definition of an eigenvalue is the values that make SI minus A, the determinant of that, equal to 0. So the big takeaway is the eigenvalues of our A matrix are the same as the poles of our transfer function. And thus, they are going to demonstrate the same stability properties that we saw before. Now, if we go to how we were finding the poles earlier with our transfer function, we know that the poles of a second order system were always going to be this negative zeta omega n plus minus the damped frequency. So there's a relationship between those response parameters, natural frequency and zeta, and the poles of our system. Very briefly on the previous slide, the eigenvalues of A, that's what the lambda is, the eigenvalues of A are the poles of this system in transfer function form, so the eigenvalues of A are also always going to be this negative zeta omega n plus or minus the damped frequency for a second order underdamped system. So if we know the properties of the eigenvalues of that A matrix, we can also make assessments about the stability of our system. So if the eigenvalues are in the left half plane and they are complex, therefore our system is underdamped. It's stable and it's underdamped, exactly the same way we looked at the poles of our system and made that assessment. And both of these are coming back to that time domain solution, homogeneous solution, where we had those exponentials raised to different powers. So when we know the eigenvalues of our A matrix or the poles of our system for our second order system, then we can find these relationships. When they are complex, the real part of the pole is negative zeta omega n, and then the imaginary part of the pole or the eigenvalue is the damped frequency. And we can use these values to figure out the parameters of our system. So one, if we just take the magnitude of our eigenvalues or of our pole, or the absolute value of it, that is the natural frequency. Once we know the natural frequency, then we can go up and find the zeta value. So we can go back and forth between the poles and the damping ratio, the natural frequency, by knowing these relationships.